probably recognize this sketch known as Vitruvian Man. It was created by Leonardo Da Vinci, a name you almost certainly recognize. Da Vinci was a renowned polymath. He achieved great success both as an artist and an engineer. For much of his life, he was fascinated with human flight. And this is a sketch of a flying machine that he devised. Although he was lauded as a great artist and engineer, he didn't really have the same renown as a scientist. I think he lacked a formal education in mathematics, and he didn't really gain knowledge by way of the scientific method. One case in point was how he perceived the way in which things fall under the influence of gravity, which obviously would be an important thing to know about if you were going to design some sort of contraption that would allow for human flight, right? If it failed, something's going to plummet to the ground. So instead of actually conducting an experiment, Da Vinci just thought about it, and he understood the concept of acceleration. So let's say an object started with an initial velocity of 0 and fell through the air. And we say it covers a distance, whatever this happens to be. Whatever that distance is. Doesn't have to be a meter or a foot or any value in particular. We can just call it 1 unit. So when things accelerate, well, first of all, when things move with a constant velocity, then they travel the same distance in every interval in time. So Da Vinci knew full well that objects don't fall like this, always advancing the same distance in each time frame. Da Vinci thought that an object would fall like this. If it fell 1 unit in the first interval of time, then it would fall 2 units in the next interval of time, and 3 units in the next interval of time, and 4 units, and so on. Now that looks like accelerated motion. So in a way, Da Vinci was on the right track, but without a mathematical upbringing or an appreciation of the scientific approach, especially in regards to conducting an experiment, then he drew a false conclusion. Galileo had the same question, and you might remember from our first lecture, Galileo came up with his notion of inertia based on rolling an object down 2 ramps that were inclined at somewhat different angles, and found that no matter what, a ball always returns to the same height. Well, he did another experiment involving ramps in an attempt to answer this same question about how far something progresses when it accelerates under the influence of gravity. Now, Galileo knew full well that if he were to just drop an object vertically, just like Da Vinci, that it's going to fall successively greater and greater intervals in even increases in time. But he didn't have sophisticated timing devices like we have the luxury of using, so it'd be very difficult to keep up with the motion of an object if it were just to fall straight down vertically under the influence of gravity, because it would fall so far in a relatively short amount of time. So Galileo was clever and realized even when a ball rolls down a ramp, if I put a ball at the top of this incline, gravity is essentially the only force that's responsible for making it roll, but by putting it on an incline, you're only capturing a component of the acceleration due to gravity. So in effect, it sort of slows down the whole process and made it easier for him to come to his scientific conclusions about the way in which an object advances. Now, he could start with an incline that's not too terribly steep. What he found was if the marble rolls 1 unit in the first interval of time down his ramp, then in the next interval of time, it would roll not 2, but 3 units. And in the next interval, it rolled even farther. It rolled 5 units. So Da Vinci was on the right track, he just had the wrong numbers. It doesn't progress as 1, 2, 3, 4. It progresses as the odd integers, 1, 3, 5, and you could probably guess if my ramp was longer, then in the next interval it would go 7. So Galileo could make his ramp even steeper. And he found regardless of the particular angle of the ramp, no matter what, as it gets steeper and steeper, it always continues to hold up that same pattern. If it falls 1 unit in the first interval, then it goes 3 times as far in the next interval, and 5, and so on. It got to a point that his ramp became so steep that he couldn't accurately time it, but he understood that no matter what the angle was, it was always the same result. So if you project it out, even if the ramp became so steep that it was practically vertical, he was certain he would get the same result. And so in fact, he realized that if you were to drop something, the same thing would happen. If something were in free fall, it would fall 1 unit in the first interval of time, 3 units in the next, 5 units, 7 units, 9 units, and so on. Now, something you may or may not have picked up on did not get past Galileo. He realized there's more to the story than this. Instead of just talking about the distance fallen within an interval, Galileo was concerned with how far the object fell from the initial starting point. So after 1 unit of time, it fell 1 unit of distance. But then if you add another 3 units to that, then the total distance from the point that it was released is 4 units after 2 time intervals. And then if you add to that another 5 units of distance, then the total displacement from the point where it was released after 3 units of time would be 9 units of displacement. And then if you add 7 to that, you would get 16. And remember, within the next interval itself would be 9 more units, which means the total distance fallen, if we add 9 onto 16, we get 25. Now you're seeing a pattern that's very interesting, right? 1, 4, 9, 16, 25. Galileo realized then that the distance fallen vertically, now so far in our kinematics equations we've been saying delta x is equal to v initial times time plus 1/2 at squared and so on. Now that we're talking about free fall and objects that are going to move vertically, we'll just change the language a little bit and say delta y. So we know this kinematics equation, delta y equals v naught t plus 1/2 at squared. I'm not sure that was known to Galileo. In fact, I'm quite certain it wasn't. But let's take a look. Knowing this, if we're talking about an object that was released from a state of rest, that means the initial velocity is 0, so we can cancel that out. So the vertical displacement overall from the point that it was released is equal to 1/2 at squared. Because gravity is causing the acceleration, that happens to be a constant acceleration, and 1/2 of any constant is itself a constant. So what we're really saying is, oh, and by the way, delta y is the same thing as y minus y initial, but if we just set our origin as the point of release of the falling object, then y initial is equal to 0. So in that case, there's no distinction between delta y or just the symbol y itself. So let's look at this. Y is equal to a constant multiplied by time squared. That's just saying that y is some function of time such that it depends on time, not to the first power, but time to the second power, time squared. And that's exactly what Galileo's law of odd integers seems to say, that the distance fallen, which is our value of y, follows the perfect squares, 1 unit, 4 unit, 9 units, 16 units, and so on. So in the end, Galileo's law of odd integers is perfectly consistent with the kinematics equations we know. And as we progress into this study of free fall, we're going to change the notation slightly, and instead of talking about displacement along a horizontal axis, we'll talk about displacement along a vertical axis. And we will probably very well stop using A as the symbol for acceleration and replace it with G, as long as we're talking about an object that truly does fall vertically and not so much rolling down a ramp. Because we know the value of free fall acceleration is 9.8 meters per second. So I have another insight on Galileo's law of odd integers I want to share with you. I've taken two chain links, taken the links apart, and then tied them back together with pieces of string. So I made it one time where all the pieces of string were the same length. And I think I have either, I don't recall, 6 or 7 chain links. So let me draw this out. I have a video I want you to watch after you watch this lecture. That's chain link number 1. And then the other one, I took all the chain links and I tied them together in a different fashion. The first two were tied pretty close together. The next two, a little farther apart. And the next chain link, even farther apart. And the next one, even farther still. And you get the idea. Now, I bet you can guess, if I say this is 1 unit, then hopefully I drew this correct. That's also about 1 unit, 1 unit, 1 unit. So I just kept the spacing consistent. And I tried dropping this chain. I climbed to the top of the staircase. And I let the bottom link just hit the floor. And I listened really carefully. And when I dropped it, the pattern I heard was, right? Ding, 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 ding. You could hear the acceleration. You could hear the rate at which each of the chain links was falling, got greater and greater in speed. So to offset for that, to try to make it so that when they hit the ground, it sounds like ding, 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 an even pattern, I had to account for that acceleration by putting the chain links farther and farther apart, the higher and higher up they went. So the distance between the first 2 chain links is 1 unit. You can guess what the distance between the next 2 is, right? 3 units. And then the next one, 5 units. This is, after all, called Galileo's law of odd integers. So I tried it. And I listened. And, well, I'll let you be the judge. So after watching this video, watch my next video where I've recorded this demonstration and see if it appears that the cadence at which the chain links hit the floor is a sort of even beat.